Any questions? Get rolling. Okay, so
Maybe I will try.
I think they're still on about the 3-line proof.
I said, I think if you have a 3-line proof of the Riemann hypothesis, you have the job anyway. They bring something here like, yeah, like use that to, or like, if you hire me, I'll show you next slide. Put all the slides with this.
make sure you publish it, yeah. You know, 3-line proof of the Riemann hypothesis will for sure get you that job at Harvard. So maybe reveal it there, but there are some places that are like, what's this Riemann thing? So, you know,
Yeah.
I had a friend that gave a talk one time on a job interview many moons ago. And when they introduced him and read the talk, they referred to his talk about DD kind domain. So, I mean, I don't even know why you don't ask that question.
Yeah. My favorite. No.
605. Okay, so this was I talked about this theorem in the next theorem last time, and I skipped over the proof just because of time thing. So let's go through this. Let me repeat the theorem. What are the Noetherian I and R an ideal, a finitely generated, R module, and B just any submodule of A. So that's kind of the setup here. So we've got a Noetherian ring, an ideal, which of course must be finitely generated by the hypothesis on R. A is a finitely generated R module, and B is a submodule. If C is a submodule of A, containing IB and maximal with respect to the property that C intersect B is IB, then I and A is in C. So C is a submodule of A containing IB and maximal with respect to this particular property. Notice that, of course, if C equals IB, then this property is satisfied, right? So C just happens to be maximal with respect to this property. You can actually use Noetherianness or Zorn's lemma argument to show that such a C must exist, as a matter of fact. Let's go through the proof of this. So of course, what we want to do is show that I to the n power times A is in C. So proof if X is in I, what we need to do is so let me kind of explain what this is true. If X is an I, and since I is finitely generated, what we need to do is show there is an M such that there's some natural number M such that, X to the M times A is in C. So to this end, all we need to do is, since I have finitely generated, it's generated by some finite set, right? And so if for each of these generators, I have some power of that generator, since it's an A, since there's only finitely many generators, I can therefore find a universal one that knocks over, that makes this true, right? So for example, if N is this universal maximal one that we have here, then certainly I to the N will be contained in A, right? Because anything in there will be well, big enough power of any generator times A is C, and so and since this is true for all I and I, we've got that taken care of. So what we're going to do is we define so I'm going to define the submodule Dn submodule of A this is going to be all A and A such that X to the N A is in C. So for this fixed A, what we do is we collect every A such that A is conducted into C by X to the N power, right? Now notice that if A is conducted by X to the N, then it's certainly conducted into C by all higher powers, right? And so what we have here is an ascending chain of modules. So, well, we see these DNs form an ascending chain of submodules. Of A, or finitely generated R module. And so at some point, they must stabilize. When we say this chain stabilizes, at M. And so I'm going to now make this claim that X I guess it's quite I'm going to now make that claim X to the M times A, where M is a place where it stabilizes. X to the M A plus C intersect B is equal to IB. So we've got this containment here. Certainly IB is contained in B. And of course, IB by definition is contained in C, so it's contained in this bigger animal, right? So the containment of, the right side and side of the left is pretty easy. Now. Right, so. Right. Now, let's get the other containment. So suppose that you have an element on the left side. So that is to say, suppose. Say, suppose T is in X, the M, A. So in particular, T is in B, and T is in this animal as well. And so we will write XMA, XM little a plus C, where of course I mean for little a to be in A. Then now, if I multiply that by X, notice this is in XB, because of course T is in B. And X is contained in I. Or XB is contained in IB. And IB is contained in C. Right. And notice this piece is in C as well, right? And so that means that X to the N plus 1 right? And so what does this mean? Our choice of M being the stabilization. This means that X to the M times A is in C. And so if X to the M times A is in C, this means that T, where was T? Well, that's in C, and C is in C, of course. And so T is in C. Therefore, T is an element of B, and it's an element of C. Which is IB. So now we have the equality of these sets here. So oops, my bad. So now we've got that equality of sets here. But C is maximal with respect to this. Therefore, we have C intersect B as IB, and now we've got something here that's potentially bigger, intersecting B equals IB. But C was maximal with respect to this property. So we must conclude that XM A is contained in C. And so, we've proved this therefore for every X in the ideal, and by our earlier argument, that means that we've got the result we want. Okay, any questions on that?
Just had a quick one. Could you explain bottom right hand corner on the board over there? Could you explain again why IB is contained in that?
Let me look. See, it's some module. Okay, good. C contains IB, right? So IB's in this piece, because this piece is bigger than C. So IB's here. And of course, IB is contained in B itself, because B is an R module. So anything in I is in R. So this multiplication here is inside B. So it's in this piece. Okay. And here is the Krull Intersection Theorem. We're going to depend on this one a little bit. This is a rather famous one right here. Here's the Krull Intersection Theorem. What it says is, if R is Noetherian, I is an ideal, A finitely generated R module, and B equals the intersection of I in A right? So here's like a really sloppy way to think about this. This is what you would hope. Intersections and multiplications are related. They're not the same, right? Multiplying two ideals in general is contained in intersecting, but if you're kind of sloppy, think about multiplying this. This is what you would hope happens. Multiplying this by another I doesn't affect this thing that's already in I to the n times A for every natural number n. So let's tackle this one. So I'm gonna leave 65 up there as long as I can. So let's prove Krull Intersection Theorem. So among all submodules of A containing IB, exceed the max. With respect to this property. Where here we'll of course use the notation here B is this. Right. Well, let me point out, so how do you how do you think that, so the first thing we do is we have our A, we've got this whole setup here. We've got A, it's a finite general R module, and then we take I times A and I squared times A and I cubed times A, all of these animals. We intersect this, we call this B. All right, which is some, I mean, it's at least 0, but maybe bigger. Now, what I do is among all submodules of A that contain I times B, because certainly A does contain I times B, pick C to be maximal with respect to the property that C intersect B is equal to IB. Right? Certainly this is not a vacuous thing to do, because notice if you take C to be IB, then there is some submodule, namely IB satisfies this. And now we figure maximal. Now this sounds very much like a Zorn's lemma thing, where we're going to sit here, and you can certainly do that. However, A is finitely generated. We have these sending chain conditions, so we don't really need Zorn's lemma for this here. So such a C exists, and you don't have to throw the actual choice at it if you don't want to. Our previous result, we have that I in A is in C. There's a natural number, lowercase n. But as B is contained in INA, whatever it is, right? Because in fact, B is contained in every INA, so it's certainly contained in this one. It must be the case that B is contained in C. Because of course C contains. But as C intersect B is equal to IB, it must be the case that right. And there you go. So that's the Krull intersection theorem. Okay. Any questions? Does anybody know is Hago Rolo that's that fancy chalk that they don't make?
No, they make it, so a company bought, the original company went out of business and somebody else bought them out, so they are still producing it.
Did they go out of business because they got bought out, or did they?
No, they were going out of business and mathematicians everywhere started hoarding their chalk. I've seen videos of people that had closets of just stacks of chalk. Of their brand.
I think they went out of business,
Survivalist mathematicians.
and then years later, a different company bought the formula that they were using.
I don't think it was too long after that. But I remember what it originally was.
Well, it's like,
There
I
was
would
a
pick that up and use it, but I can't help but think that somebody left that there, and I feel all guilty about using it.
If they don't, it's their fault.
It's like the mathematician version of when they stopped making cookies for a little while.
And then I started making them again.
Yeah. I'll break it.
Snowballs.
Okay, so, we're gonna introduce this theorem. This actually is gonna help us, when we get to, down the road here, Nakayama. So suppose we have a ring, I and R an ideal, and A and R module. Yeah, there's a lot of these caveats in here. Ring, I and R ideal. A in generated R module. And X an element satisfying. I want XA to be an IA, don't I? Then X to the N plus Y comes A. Is equal to 0 for some Y and I. Okay, so let me so this has got these theorems always confuse me a little bit. There's so much stuff I try to start being an accountant, keep track of it all in my brain pan here. So same setup as the last few. We've got a ring, we've got an ideal, and then we've got this in generated, and I guess that's going to come into play here. R module. Now X is an element satisfying XA is contained in I, right? Now nobody said that X had to be an A. Right, I'm sorry, nobody said that X had to be an I, right? Notice that this is trivially satisfied if X is an I. Right, so X is sort of mimicking the effect of some element in I, so to speak. What happens, so what it says is, then a sufficient power of X, namely however many generators they have, a sufficient power of X plus some element of the ideal times A should be 0. For example, what happens if X itself is already an I? Then in this particular case, I guess you could just take N to be 1 and Y to be negative X, right? If it's already an I, right? So this is sort of measuring how close a power of X is to sort of being in Y, loosely speaking. So let's go through the proof of this. Sure.
So in the case that X is not an I, how do we know that there exists such an X such that XA is an IA?
We don't,
Okay.
right? So, well, we do actually. I mean, for example, you take X to be 0, right? Because certainly 0 is an element that is satisfied, right? So, but all we're saying right here is just suppose it's got that property, right? And of course, that's a good question. What happens if, for example, X equals 0 here? Well, that would be a big fat 0, and then you can just take Y to be 0 as well. Right? Yeah, by the statement of the theorem, it doesn't claim that X is that such an X exists, but it does. All right, so let's so we know that A is in generated, so let's do this. Okay, suppose that A looks like this. And what else do we know? This looks very much like when we proved integrality in that module condition. What do we know? We know that X times A is contained in IA. So when you multiply X by any of those generators, so X times any of those generators that I have over here should be able to be expressed as some linear combination of crap and I times crap and A, right? And again, I can use the same generators for A. So let me try to write this out. So there exists, let's say, Y, I, J, and I. So these are just some elements that we find to make this work. Such that XAI. Well, of course, XAI is an element of XA, and so I have to be, this has got to be in I times A is YIJ AJ. Let's say J equals 1 million. Right? And that's just a statement here that X times A, this has to be a linear combination of crap and I times crap and A, and I can just replace the crap and A with its generator, so streamline it right that way. Right? And so what we have is, just like in our proof of integrality, this gives us a system of equations. That I'll write out. Let me write this down and then check to make sure I got it right. See, X minus Y11 A1 Y12 A2 minus Y1N AN. Yeah, these are all just you see, but this is minus Y21 A1 minus X minus Y22 A2 minus Y2N AN 0. Yada yada yada. YN1 A1 minus YN2 A2 minus plus X minus YNN AN is equals. Okay. So notice we can use some linear algebra here. The determinant of making the system annihilates all the AIs. And is of the form X to the N plus Y. Right, because when you go through this determinant, right, if you're like, if you take the determinant of this, you get sort of a polynomial in X. It's going to lead out with the term X to the N, right? And notice that every other term has one of these YIJs in it, right? Every other term does, right? only the x to the n is naked, everything else picks up a factor of y, so. And that's all we need, because x to the n plus y, that's of the claimed form here. And it annihilates all the AIs, so it's gonna kill all of A, it's gonna kill all the finite, the n generators, and so. That's kind of I like that, it's kind of a slick little thing. Okay, any questions? Okay, so good, I guess that's 607 up here. So let's do this corollary. I can never resist kind of the cool looking corollaries. Let's apply this to the case where x is equal to 1. Right? It's always good to check what happened in case x is 1 here. Let R be a ring and I an ideal. Ideal. With the property that, oh, I need a finitely generated module satisfied. Satisfying that IA is equal to A. Oops, I'm sorry. Certainly, you always get this containment. And to get the other containment is similar to this. Then in fact, the finitely generated R module, finitely generated R module A is annihilated by an element form 1 plus 1 plus y, right? Because that's exactly this theorem here applied to where x is 1, and we're generally a unit. Because in this case, what you have is you have A is contained in IA, and the other containment always happens, which is this condition right here. Okay. Any questions? Let me give you a definition that I think that most of you probably know anyway, but it's not gonna hurt me to repeat it here. Definition 609. Let R be a domain and A an R module. We say that A is torsion free. If XA equals 0, here I mean X is in R, A is in A, implies X equals 0 or A. By the way, so torsion free, what it means, for the module to be torsion free is, it has a torsion, and what is a torsion element? A torsion element is one, we'll say X is a torsion element if it is well, actually, we'll say that, A is a torsion element if, there's a non-zero element of X that kills it, right? So it's torsion free if, only zero is killed by stuff that's not zero, right? That's what it means. Does anybody know why we throw domain into this definition? Right? I mean, so here's the thing. You can call an element in a module a torsion element if it's killed by a non-zero element of the ring, right? What's the difficulty if the ring is not a domain?
You take two zero values, multiply that zero, multiply one of them, and you multiply the other, and then
That's right. So, for example, one of the problems, and you can do things more generally, but the reason that we do domain here is if you look at a torsion element, right? Then, right. So it is, the torsion elements may not be closed under addition if you don't have a domain. So let me give you an example. Consider let's see what's so if you look at Z6, and here of course is a domain, then all elements of Z6 is a Z modular torsion, because if you take any element from Z6 and you multiply by 6, you get 0. Now, what happens is and this is not a domain, right? So here's kind of the problem here. Notice that in R as a module of itself, two bar, consider that as a module element here, times 3 bar is equal to 0 bar, right? So 2 bar is a torsion element of this module, right? Also, three bar is a torsion element of this module, right? So the reason that it's a little bit wonky in the non-domain case is that 2 bar plus 3 bar is 5 bar, which is not. Because multiply this by all elements of Z6, and what does it take to get 0? If you multiply this 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, you don't ever get 0. this is not a torsion element. So the problem is if you have an integral domain though, then the sum of two torsion elements is still a torsion element, right? Because in a domain, if T1 and T2 are torsion, R's are elements of rings and T's are torsion elements of the module. Then notice that T1 plus T2 is also torsion, right? And the failing if you're not a domain, because notice the product here is certainly zero, right? And if you assume R1 and R2 are not zero, then R1, R2 is not zero. Now, this doesn't happen here because what happens is what it took to kill 2 and what it took to kill 3 basically generate a unit, right? Because they generate a unit additively and the product of them is zero. Right? So anyway, that's what it does. So we're going to say that we're going to find A to be torsion free over domain if this happens here. The only thing that kills a non-zero element is a non-zero element of the module is a zero element of the ring. Let me give you the following proposition here. So let's suppose R is Noetherian. We're gonna need that here. And we use that word a while, we need it. And I have a proper ideal of R. And R proper ideal. And a finitely generated torsion free R module. And we want A to be finitely generated, we want it to be torsion free. Then the intersection if you intersect all of these sheets. Okay. I think I just had time to prove this. And we're going to use the previous couple of results on this. So let B equal. Of course, our goal is we want to show that B is in fact exactly zero. We know by Krull Intersection Theorem that IB is equal to B. Right? And by the immediate previous one, that one plus YB is equal to zero for some Y and I. And that is our immediate predecessor theorem. But this is torsion free, so either we have that B equals zero, or y is equal to -1. Oh, I'm so sorry. And of course, I saw that here at this point of proof, and then, and the theory don't matter, that's. We need that. Can't see either b equals 0 or y equals -1. But y equals -1 is impossible. If I is proper. That's the ideal, proper ideal can't be made. Okay, any questions? Any questions out there? All right, well, y'all consider checking out the math club this Friday and stay dry, and we'll see you on Friday.
Is it raining?